Hi, I'm Professor Johnson, and in this video we will be talking about the process of science. So first of all, what is science? Well, science is a way of knowing. We can divide science up into two major categories, the one being the really descriptive and observational science, and the other being the hypothesis-driven and experimental science. So descriptive science involves making observations and measurements and really getting to the point of describing the world better and better. However, where science is really predictable is when we actually start designing experiments and testing experiments that can tell us about, allow us to make predictions about the future or really deduce what's gone on in the past. And in doing this, we are using both deductive and inductive reasoning. Deductive being going from general concepts and making specific predictions with them. So this is more of the process of the scientific method where you're actually testing the predictions. And here, going with using inductive reasoning, you're going from specific to general. So it's really the part where you're really forming hypotheses, forming theories, and really then testing them with different experiments. So the scientific method is going to use both of these in sort of a forward and backwards direction. So what is the scientific method? I'm sure you've seen many ways of depicting the scientific method, and all of them are valid and have different weaknesses and strengths. This is the one I prefer. So with this, you're going to start with observations and questions. So your questions are really going to inform what you go out and observe and learn, and what you observe and learn are going to help you develop questions. So it's hard to really put one before the other. Sometimes people do, but both of them are really going to be used then in developing your hypothesis. So your hypothesis is really a testable answer to the question that you generated. And then once you have your hypothesis, you'll find that there are certain predictions that can come from your hypothesis. These predictions then allow you to make or design an experiment. And the experiment will give you results that allow you to come to conclusions. The conclusions either being that your hypothesis is supported. Notice that I did not say that your hypothesis is proved. You can't actually prove a hypothesis with the scientific method. In science, no proof is absolute. We can only gain more and more confidence in it with further testing, but there is no absolute proof that can come from the scientific method. Of course, it's always possible that your hypothesis won't be supported, in which case you might test a different hypothesis going along. So how this may occur is you may one day walk into your living room and try to turn on the TV with your remote, and you'll observe that your remote isn't turning on the TV for whatever reason. So you might generate the question of, why is your remote not turning on the TV? So a hypothesis that you might come up with is that the batteries in the remote are dead. So a prediction you might make is, if you change the batteries, then the remote will work. The experiment's pretty straightforward. You would change the batteries, and then the results of the experiment would be whether it did in fact fix the problem, so it might have solved the solved the problem, and then in which case your hypothesis is supported. Or if it didn't work, you might have to generate new hypotheses. Maybe all of the batteries are bad, and so you have to go out and find more batteries. Or maybe the TV is unplugged, or maybe the remote is broken, or maybe the TV is broken itself. So there are lots of different hypotheses that can be made. And hypotheses can generate more than one prediction. So one hypothesis can be tested by many different types of experiments. Now you'll notice that I actually made a distinction between a hypothesis and a prediction. And not everyone does this. I believe it is an important distinction, so I'm holding you accountable for it. But a scientific hypothesis doesn't need to be stated as an if-then statement. An if-then statement really is a prediction. If this is the case, then this will happen. A scientific hypothesis is the tentative answer to the question. So with the previous example where we asked why won't the remote turn on the TV, you might look at these and say, okay, these are hypotheses that are generated from it. If the TV won't turn on, then the batteries in the remote are dead. If the batteries in the TV are dead, then changing them will fix the remote. And then the final one I put on here, the TV won't turn on because the batteries in the remote are dead. So really your hypothesis here is that the batteries in the remote are dead, and it's part of all of these statements, but your prediction is really what these are saying. So here, if the TV won't turn on, the batteries in the remote are dead. This is really the prediction that you're making here, and this is really sort of an observation and then your hypothesis. So this really isn't even a prediction. It's in the second one, it's really more of a prediction. If the batteries in the TV are dead, then changing them will fix the remote. So this would be a prediction that would come from the hypothesis that the batteries in the remote are dead. And then the final one, the TV won't turn on because the batteries in the remote are dead. So the batteries in the remote and dead in this example are your actual hypothesis. So there are a lot of different things that can come up with an experiment. And a lot of these things are variables. So variables are anything in an experiment that could possibly vary. There's two important variables that you want to pay attention to. One is the independent variable, and the other is the dependent variable. Now, the independent variable is going to be the thing that I, as an individual, change, whereas the dependent variable is going to change depending on the independent variable. So if the independent variable has an effect on the dependent variable, it will change. Usually the dependent variable is going to be put over here on the y-axis, and the independent variable is going to be what you put over here on the x-axis. So in this case, the year in school would be on the x-axis. That would be your independent variable, and the number of college classes taken would depend on your year in school. So this is going to be on the y-axis. Now, controls are different things that could vary in your experiment, but you don't necessarily want them to. So it may be that you are trying to determine what causes the number of college classes to be taken, and you may be looking at year in school, but you may also want to control for gender. Maybe males tend to take more than females, what have you. But they're just different things that could possibly vary an experiment that you would want to account for and control for. Now, there are two specific kinds of controls that can happen. One is a positive control and the other is a negative control. A positive control is really an experiment that you know is going to end up positive. So it's an experiment where you know the outcome will happen. And then the negative control is an experiment where you know the outcome will not happen. So if you don't get a result in your positive control, that would indicate that something went wrong. And if you do get a result in your negative control, that would also indicate that something is wrong. And then we talk about these as being individual controls. Sometimes you have a control group and a test group. So you can look at these being split up into your control and your variable, or you can divide them up into groups. So you can have your control group where you're keeping everything the same. You're not manipulating the variable that you want to test. And then with your test group, everything else is the same except for the one variable that you want to test, your independent variable, which in this case would be called your experimental variable. And then you'll see if that has an effect by looking at whether the control group had a different response than the actual test group. So let's look at another example. So you may have a question, how can students be better prepared for exams? I, as an instructor, want you guys to do well on exams. I'm sure you as students want to do well on exams. So this might be a common question that is actually applicable to you. So you may make observations. For example, students spend a lot of time rereading notes in the book, but they don't necessarily do well on exams. And then you may think that, or you may also observe that students who quiz themselves over the material covered in the lecture do better on the material that they are quizzed on compared to the information they're did not quiz themselves on. So based on these observations, and these are observations that people have made, you might actually develop a hypothesis where frequent quizzing over material arrests forgetting prepares students to do well on the final exam. Now your hypothesis can have several predictions. For example, if this is your hypothesis, you might predict that students that quiz themselves regularly will do better on exams. You may also make a prediction that if the instructor includes frequent low-stake quizzes in his classes, then the students will also do better on exams. And then finally, you may make this prediction that in the same class, if the students were exposed to material repeatedly, some of the material via quizzing and some of it via reading, then you may predict that they will do better on the exam material that was reviewed via quizzing, with the feedback telling you that you got the question right or wrong, compared to just reading the material and being exposed to it again. So let's look at the same prediction. So in this class, if the students were exposed to material repeatedly via quizzing, that's what this over here is looking at. So you might have a topic in class that is looking at what a hypothesis is. And so you're asked to get this material outside of class on your own, and then in class you would be tested over it, and you would on a low stakes format, and you would then have that material being what you were quizzed over. Alternatively, you may have another set of material, such as a theory is a proposed explanation for a natural phenomena, often based on some general principle. So this is me telling you what a theory is. You will be exposed to it again in class, but you won't actually be asked any questions about it. So you won't try and recall this from memory. You're just being exposed to it more. So with this, you're thinking that you would take a test with the material over hypotheses and then material over theories on this, and you may then see, okay, what percentage of the material reviewed by quizzing, what did the students get correct? And over here you might see that 75, whereas the rereading material, where you weren't actually pre-tested over it, you only get a 55%. So you do better on this topics reviewed by quizzing than versus rereading. Now, this isn't just a hypothetical experiment. There have been numerous times that this experiment's actually been performed. So this is why in my class we will be doing a lot of practice recalling information from memory and answering questions that will be similar to what you are exposed to on exams, versus just having the material being force-fed to you and then coughing it, trying to have you cough it back up to me. Because we've seen through numerous studies that that is not an effective way for everyone to learn. Well, this method does do a lot better of getting everyone there to reading. So now that this prediction has really supported your hypothesis in this experiment, you might then go back and look at other predictions and design other experiments to test this hypothesis and really prepare yourself best for it. So another case would have been if the hypothesis was refuted, you might have went back then and looked at different hypotheses about how students can study. And obviously in this case there are hypotheses that aren't necessarily exclusive from one another. And ultimately you may go about developing a grand overview of how students learn. And this could be called the theory of learning. So notice here that I'm not saying that a hypothesis graduates into a theory. So hypotheses for the most part, and maybe universally, don't actually ever become a theory. You can't prove a hypothesis to become a theory. But multiple experiments can come together and ultimately give enough strength to an idea that this idea then can be thought of as a theory. So a theory can be sort of thought of as a mental model that really explains some aspect of the natural world very well, and it's really one of the top tier things that we reach for in the sciences. So this is very different from how you may hear the term theory used in everyday language, where people are saying that they have a theory about something, and they mean that they have a guess about something. It may be a wild guess, it may be an educated guess, but that's really not what a scientific theory is about. So it is different from what the lay people, or what the general population use the term theory for. All right, I hope this was informative to you, and I will see you guys in class.